Okay, let's have a look how transformer short circuit current is calculated. Before that, we should be able to calculate the rating current of the transformer. Okay. So, for example, if we take as an example 400 kV transformer step down to 130 kV. Okay. So if the first thing what we need to know is how to calculate the primary current and secondary current of the transformer. To do that one, we have to look at on the 400 kV side, for instance. So we have to look at the full load current, is calculate MVA divided by √3 times kV, which is say for instance 346 in this case. Okay. And then if we look at on the 132 kV, which is on the LV side, the full load current, the full load current is also obtained as same formula, so which is 1050. Okay, so what we can check on this one is just the turns ratio basically. So if we compare, or if we divide the ratio of voltage 1 divided voltage 2, primary voltage over secondary voltage, which is equal to secondary current times over primary current, so that the turn ratio is basically 3. Okay, so if we divided this, divide the secondary divided by the primary current, so the ratio is 3. So from that, we can calculate the short circuit of the transformer. For example, if we look at on here, so this ignore the CT, the CT rating. We normally choose based on the nominal current, for example, which is higher than this value, because 346, we can choose 400 or 500, but the nearest or the appropriate CT ratio will be 600, and then on here above 1050, normally like 1200 or 1100, but say for instance 1200, but this is not the topic for now. Okay, so for example, like how do we calculate the short circuit current for this transformer? Well, the first thing what we need to do is we need to look at the source impedance first of all. What is the source impedance of the transformer, or the source? And the second one is what is the source impedance related to the voltage, so that at 400 and 132. Okay, and then from that we can calculate the volt current on 400 kV and on 132 kV. So on 400 kV on this side and then on this side. Okay, so let's calculate the source impedance, because what we need is in transformer or in a power network, whatever, we need to have a source impedance, and if we have a fault in here, for example, because the generator is acting as a main source of the current or the fault current. So the current will come to the fault point. So we need to be able to calculate either this ZL or ZS and Z source on here, okay? Or whatever, the total, we can say the line plus transformer. So for this case, we have to calculate the source impedance, which is the source impedance of the generator in here, okay? So for that reason, if the source impedance calculated V square over MVA, rated MVA of the generator, because the generator is, okay, we ignore the in here, we assume 400 kV, like purposely or assume it. So for 400 square divided by the fault level or short circuit capacity of the generator is 43648 MVA. So that now the source impedance is 3.67 ohm. Similarly, we can calculate the Z transformer, which is this one. It's the same, but we just have to calculate by the ratio or by the by the percentage of the linkage reactance or transformer reactance. So 400 or kV squared divided by MV times 8/100, so which is 53 ohm. Okay, from that we can calculate the impedance, source impedance referred to the 130 kV, and then we just change the voltage value. Now we have 0.33, and similarly the transformer as well, and then 5 ohm. Okay, so from that, what we can do is we can calculate the three-phase fault at F1, which is this one, which is the maximum three-fault current, which is referred to 400. So for example, we have a fault, but how much fault current will be referred to 400 kV. For that one, normal fault current is calculated voltage divided root 3 times the total impedance until the fault point, this fault point, for example. So until this fault point, the total current. Okay, current, because the current always comes from the source. So 400 divided root 3 times 3.67, which is the source impedance of the generator, plus the transformer impedance at 400, which is 53, this one. So now we have a 4 kiloamp. And then if we had to calculate the maximum three-fault at 130 kV, well, we just change this one, or we just multiply by the 400 divided by 132, which is the 3, the turn ratio, what we calculated. Or we can do this way as well. We can just change 130 to this one, and then we can change this one. Instead of 3.67, we change this value. And then instead of 53, we just change this one, this 5.8. Then we can get 12.28 kiloamp. So that, or the other way is we can calculate by the turn ratio times the fault current of the 400 at the 400 kV side, okay, which we get 12 kiloamp. That is 3 times at least than the so if we look at the turn ratio again, 12.28 divided by 4.045, which is around 3. So that's the same as the turn ratio. So this is what we are more interested. We need to match the turn ratio so that we can say, okay, whether this is a voltage or current, it must be true. V1 divided by V2 is equals to I2 divided by I1. So 400 divided by 132 is equals to I2, which is 12.28 divided by I1, which is 4, so that the turn ratio is 3. And so, but to analyze the easiest way to analyze the fault current is we need to be able to see what is the impedance of the transformer, for example. So for example, in here it is 8%. So that what does this mean is the transformer is capable of passing 100 divided by 8, that is 12.5 times the rated current. Okay. So for example, the primary rated current is 346. If we multiply 12.5 times 346, that is around 4 kiloamp. Okay, and so that is I1, and then I2. IF2 now, the fault current on the secondary side, that will be again 12.5 times the rated current of the secondary, that is 1050, and then this will give me 12 kiloamp roughly. Oh, okay, so that's what it can match. This will match, sorry, with this one, and then this it matches with this one. So if we look at the ratio, then we can IF2 divided by F1, that will be 12 divided by 4, that is still 3. Okay, so that's again true. So what we try to say is the easiest way is if we have the transformer impedance and then the MVA rating, then well, that means the easiest way is like that means the transformer is capable of passing 12.5 times the raised current of the transformer. Okay. So either we can do this way or we can do all this way. Okay. This calculation, these steps. Okay, thank you. Cheers.